Hello everyone, welcome back to another series, and today I would like to solve 2004 USAMO problem number 5. USAMO problem number 5 is actually really hard, and this problem was actually proposed by one of my favorite mathematician, Tito Andrescu, so that's why I also like this problem a lot. And when I first studied this problem by looking at the solution, um, it was really hard to link from the previous step to the next step, but I will try my best to intuitively think why each step occurred. Yes, so let's start. For this problem, what we should notice is that we have a plus b plus c cubed. I think this cube is quite important. And we also know that our left-hand side, this is cyclic. So what we can do here is, what if we find a relationship between one block on the left-hand side and a plus b plus c? That way, we might be able to prove the relationship. And what I mean by that is we can just, without loss of generality, write that a is greater than or equal to b, which is greater than or equal to c. However, while I was doing this, I realized that other people had proposed a better solution than try and prove it like that. And that is using the property that our left-hand side here is cyclic. So if we somehow find an inequality that states like something here, then we might be able to prove our entire inequality here. And our right-hand side for this one, we want to minimize the use of a, and that is because let's say we are multiplying terms, and we need to prove that this is greater than or equal to a plus b plus c cubed. And notice that the degree for a, b, and c here, they're all equal to each other. However, here we have a to the power 5, a squared, and like a to the power of 0, which means we have different degrees for a. And that might actually be harder to prove. So having the differences in degree may be more difficult. So what we can do is, what if we find an inequality in this form where we have only one term that is with a. So like it can be a squared plus something, or like a cubed plus something. And in order to do that, one intuitive thing that we could think is, I think, try and use this a to the power 5 minus a squared. And what I mean by that is, when we try this, because when we do this, we will get a to the power 5 minus a squared. That's already what we have here. But we have additional term, which is negative a cubed and plus 1. So if we just add a cubed and then plus 2 on both sides, then we will just get our original one, which is a to the power 5 minus a squared plus 3. So this is true. That means we can do something from here. So we know that a to the power 5 minus a squared plus 3 is greater than or equal to a cubed minus 1 times a squared minus 1. And that is because a, b, and c are positive real numbers. And actually this works for b and c too, but I'm using a for convention, and that's because our left-hand side is cyclic. Now, our right-hand side is not in terms of only, we have more than one term that is with a, and we don't want that. We tried to change it because we didn't really like that one. So let's try and observe more on these two blocks right here. So why don't we try and graph this intuitively? So let's say we have this, and this here is a, and here's what we get, like y. So when we graph our a cubed minus 1, we'll have negative 1 here, and then it will go something like this. And obviously it will reach 1 here. And For our a squared minus 1, we can also graph it, and also it will go like this. Now, what we want to notice here is that if we multiply like our terms, so for example, when a is between 0 and 1, when we multiply a cubed minus 1 and a squared minus 1, which are like these, or anything from here, we will get positive value. So this thing is positive for a in between 0, 1. However, obviously, it will be positive if a is greater than or equal, greater than 1, and it will be equal to 0 when a is equal to 1. Therefore, we can conclude that this whole expression is greater than or equal to 0. So let's try and use these two to find out more. And the reason why we want to use this is because we can somehow change this form into a to the power of 5 minus a squared plus 3. So let's expand this first. We have minus a cubed minus a squared plus 1 is greater than or equal to 0. And because we are looking for an inequality that is related to this expression right here, let's try and convert it. So we have a to the power of 5 minus a squared plus 3 is greater than or equal to a cubed plus 2. Now this is what we wanted. So our right hand side is a cubed plus 2. We have only one term that is with a. So this is exactly what we have wanted. And now we just need to prove that a cubed plus 2 times b cubed plus 2 times c cubed plus 2 is greater than or equal to a plus b plus c cubed. And the reason is because these things are bigger than or equal to a cubed plus 2, it will automatically satisfy our inequality right here. So that's why we want to try and prove it. And one thing that I think we can do is, because we see cube right here, why don't we cube root everything, because we know that a, b, and c are positive numbers. So cube root of that, I don't want to use the root sign, times b cubed plus 2 times c cubed plus 2 to the power of 1 over 3 is greater than or equal to a plus b plus c. If we could only prove this, then we can prove our inequality above. Now let's change the form a bit. And the reason why I did this, or we can do this, is because you know that 1 over 3 plus 1 over 3 plus 1 over 3 is equal to 1, and we have 1 right here. That means this should remind all of us our Hörder's inequality. So in order to try and exploit our observation right here, we can do something like this. They're all the same. So 1 plus 1 plus c cubed 3 greater than or equal to a plus b plus c to the power of 1. And is this true? So let's use our Hörder's inequality here, and we know that this thing right here is regarding this one, we just want to explore more on our left hand side, and we can do that by considering our Hörder's inequality, and that works by using our first terms from each block, so a cubed and 1 and 1. So we have greater than or equal to a cubed to the power of 1 over 3, 1 to the power of 1 over 3, and 1 to the power of 1 over 3. And then we have plus, we do the same thing. So b cubed to the power of 1 over 3, and 1 to the power of 1 over 3. And it's the same for c. And we can notice that this is same as a plus b plus c. Therefore, we proved our lemma. And by proving our lemma, we know that because we mentioned that if we prove our lemma, our inequality above right here is also proven. And therefore, we completed our proof. Now, I think there are multiple takeaways from this problem. So I think the first kick from this is noticing that our left-hand side is cyclic. And also knowing this that is cyclic, trying to convert trying to write an inequality for a to the power 5 minus a squared plus 3 with our right hand side with only a constant term and a term with a. So I think trying to find this one was our first main kick. And also trying to graph this, I'm not sure if other people also graph this too. So actually, other solutions just mentioned this one, so I don't know how other people did it. I just thought of this one and then I automatically just graphed it. So this section is only like my solution. I mean, it's not entirely my solution, but this section is from my idea. So I'm not sure if other people did this one too. If you guys think that you have better ideas, please share. And yeah, so I think trying to graph this was also a great idea. And then writing a lemma, and then our last kick was noticing that we have cube here, and then our left hand side is also cyclic, which means we can cube root our both sides and then use our Hörder's inequality. So I think even though this problem was USAMO and problem number 5, it was actually really difficult to find the pattern and trying to go from here to here. I think that was one of the difficult parts, and then trying to notice Hörder's inequality here. So I think this problem was really meaningful to me and hopefully to everyone who is studying Math Olympiads. So thank you so much, and see you in the next video. Bye. Oh, also, please don't forget to share and like this video and subscribe if you want more videos like this. Please also share any questions or comments you have in the comment box below. No puns intended. And thank you, and see you in the next video. Bye.